All right, we now have a giant magnet here, and we have 6 or 8 strands, looks like roughly 8 strands of wire. The electricity in this wire, it's a little hard to see from that side, but we have the electricity going down in this case. Let's find out which side of this magnet is positive, or is north, and which side is south. I have a little known magnet again. Red is north, yellow is, sorry, red is north, white is south. And notice that that must be the north, and that must be the south. So the magnetic field points from north to south, which is my fingers. The current flowing, positive current flow, will be my thumb. That's the direction you're going, or as Mr. Bois says, go with the flow. So if I have the magnetic field and the current going down, it should push towards you. Here we go. So let's watch the wire. Now if I reverse the magnetic field, so that the magnetic field is going this way, current down, it should pull into the magnet. Stop. All right, once again we have the giant magnet here. We know that this is the north pole. Notice the south down, north up, and that's the south pole using a known magnet. I have a wire here that is going to go, this is the black side, this is the red side, so it's positive, this direction to negative. I'm putting this box in the way just so that it's between the poles of the magnet, like that. And watch what happens when I touch the negative terminal of the battery. Here we go. Once again, and we'll do that one more time. Putting this up here to where it doesn't have to pull the whole wire. Once again, here we go. And it throws it right out. Magnetic field. Current is flowing that direction, the force is up. But if I reverse the flow, it'll just pull down into the magnet, which in this case would not be as impressive because it's not jumping out. So we'll do this with the push down this time. I'm not even sure there's all that much to see, but I'll hold it here, maybe that gives it something to see. There you go. Stop.
Hello, my name is Bruce Yaney, and today I'd like to take a look at a device called a tangent galvanometer. This piece was first described in the 1800s as a way of detecting and measuring electrical currents. It's a simple model, and it can be made using a magnetic compass, a few turns of wire, and a battery. In fact, this is a piece that I might have my students try for themselves. So first thing is we want to take a look and see how this is built. So here's our first model of the tangent galvanometer. We have a compass, we have the wire wrapped around it, and I've positioned the needle so that it's directly underneath those wires. Now when I hook up a battery to it, we see that the needle moves directly perpendicular to that coil of wires. And if I were to turn the battery around, once again we see the needle move, but in this case it has swung 180 degrees so that we now have the needle facing in the opposite direction. But the point is it is actually perpendicular to that coil of wire. Here's my display model one more time. In this case I've hung a bar magnet down from the top of the coil. It is parallel to the coil itself, and once again if I energize this coil we should see a movement. In this case of the bar magnet, it lines itself once again to the magnetic field, which is perpendicular to the coil itself. If I release it, it returns back to the center. If I were to switch my polarity around, switch my wires around here, we will see it reverse itself. Once again, it is perpendicular to the magnetic, or to the coil of wire, and it's lining itself up to the magnetic field. And we can play around with it a little bit. Just tap it slightly and get it to swing back and forth. This was actually the precursor to an electric motor. It shows the relationship between magnetism and the flow of electricity. So anyway, this is my example of a tangent galvanometer.
Now we are going to discuss about working principle of DC motor. The working principle of DC motor is very simple. We know that when a current-carrying conductor is placed inside a magnetic field, it experiences mechanical force towards a particular direction. Let's take a simple elementary model of a DC motor. In this model, one single turn of conductor is placed between two opposite poles, that is North Pole and South Pole, as shown here. Now, if we start supplying DC through a commutator system to the single turn, current starts flowing through it. At that position, as we see, the positive terminal of the battery is connected with left conductor of the turn, and negative terminal of the battery is connected with right conductor of the turn. Moreover, we see here in the model, the south pole of the magnet is placed at left side and north pole of the is placed at right side. Current in this left side conductor flows inward and current in right side conductor of the turn flows outward. As we see, the conductors are carrying current and placed inside a magnetic field. Both of them experience mechanical force acting on them. Then thumb indicates the direction of mechanical force. This is clearly upward here. Then thumb indicates the direction of mechanical force. This is clearly downward here. Due to these upward and downward forces on the turn, one torque is produced, which tends to rotate the turn in clockwise direction as shown. After clockwise rotation of 90 degrees, the turn comes to a vertical position in respect of the magnetic field. At that position, there is no current in the conductors of the turn, as the conductor end brushes rest in between two commutator segments. Hence, there is no force acting on the conductors, but due to moment of inertia, the turn continues to rotate and comes horizontal again. But position of the conductors has been interchanged here. That means the conductor which was previously at left position comes to right position, and which was previously at right position comes to left position. At that position, again mechanical force acts on the conductors. Then thumb indicates the direction of mechanical force. This is clearly upward here. Then thumb indicates the direction of mechanical force. This is clearly downward here. Due to these upward and downward forces, the turn tends to rotate in clockwise direction as shown. Now, from that explanation, we can come to the conclusion that here in this model, whichever conductor comes under south pole experiences an upward mechanical force, and whichever conductor comes under north pole experiences a downward mechanical force. And due to these two forces, the single turn continues to rotate until the battery is disconnected. A practical DC motor rotates with same principle as of this elementary single turn model.